ഒരാളിനെ കയറിയോ കൊണ്ട് മാറാ അതോടെ 10 ആള് കയറിയതാ. ഒരു ഞാൻ 2 പേര് ഇവിടെ. ഞാൻ എങ്ങനെ ഓപ്പൺ ആക്കുന്നത്? എന്തെങ്കിലും കടിക്ക് വരൂ. ലൈവ് എൻ്റെ ആക്കാൻ മാത്രമേ വാട്സപ്പ് ഇട്ടിട്ട് ഞങ്ങൾക്ക് ട്രിപ്പിൾ ഡി ട്രിപ്പിൾ ഡി ഡീന്നടിക്കുക എന്നിട്ട് സെർച്ച് ആക്കുക. ഇതിൻ്റെ ലിങ്ക് എങ്ങനെ ഷെയർ ആക്കുന്നത്? അല്ല ഇതിൻ്റെ ലിങ്ക് ഷെയർ ആക്കണ്ടേ? കോപ്പി ലിങ്ക് ഇത് ലെവലാക്കണ്ടേ? ബിജു നിക്ക് ഇവിടെ വായിന്നുണ്ട് ഒരു ആഡെല്ലാം ഉണ്ടാവും. പിന്നെ ആഡന്നല്ലേ നിക്ക് വാട്സപ്പ് ഇടാം. ഇപ്പൊ റെഡിയാ? ഇപ്പൊ എനിക്ക് കൊണ്ടാവും. അതല്ല നിന്റെ കൈ വറക്കുന്നുണ്ട്. ഇല്ലേ വേറൊന്നുമില്ലല്ലോ. എല്ലോണെങ്കിൽ നീടെ ബാഗ് നിന്നെ എടുത്തിട്ടുണ്ടോ ലീവില്? സാറിന് നമ്പർ കൊടുക്കാം, വിളിക്കാല്ല. അശ്വത് ഫോണല്ല. അശ്വത് Azim.
Good afternoon, everyone. Warm welcome to all the dignitaries, faculty members, and my dear friends. On behalf of the Department of Electrical and Electronics Engineering, I welcome you to the distinguished EEE Alumni Lecture Series, conducted under the theme Reconnecting with the Proud Past. Before we proceed, please allow me to introduce myself. I'm Zahra Aishah, coordinator of this event, along with Mohammed Shafruddin, and I'm the anchor for this event. It is now my proud privilege to introduce today's distinguished speaker. Our guest is an esteemed alumna of the Department of Electrical and Electronics Engineering, whose professional journey stands as an inspiration to all the aspiring engineers. Mr. Yashmi Raghavan is currently working as a team leader at NCS, part of Synopsys Bangalore. With a strong academic foundation and extensive industry experience, she has been actively involved in advanced electromagnetic field simulations and real-world engineering solutions. Her expertise and passion passion for simulation technologies make today's session extremely valuable for all of us, especially for S4 students. We're truly honored to have you with us today. Now, without further delay, I request Ms. Reshmi Raghavan to take over the session and invite her to the talk.
എൻ്റെ പേര് രശ്മി പറഞ്ഞ ഞാൻ ഇവിടെ 2004-2008 ബാച്ച് പാസ് ഔട്ട് ആണ് ഇലക്ട്രിക്കൽ ഡിപ്പാർട്ട്മെന്റിൽ നിന്ന്. അപ്പം ഇന്നത്തെ ഈ ഒരു സെഷനിൽ ഞങ്ങൾ സംസാരിക്കാൻ പോകുന്നത് മോസ്റ്റ്ലി അബൌട്ട് ഇലക്ട്രോമാഗ്നറ്റിക്സ്. ഈ ഒരു സെമിസ്റ്ററിൽ നിങ്ങൾക്ക് സ്റ്റാർട്ട് ചെയ്തിട്ടുള്ള സബ്ജക്റ്റ് IVMFT. സോ ഞാൻ വർക്ക് ചെയ്യുന്ന എൻ്റെ പ്രൊഫഷൻ ഈസ് മേജർലി ബേസ്ഡ് ഓൺ ഇറ്റ് റിവോൾവ്സ് all around electromagnetics. So let me just pull out. Okay. So the major intention with which I am starting the whole session is to give you a brief overview, one of electromagnetics, and another is why you are learning all this. It's one of the toughest subjects that you will have in this whole curriculum, and one of the most important subject, I'll say. It relates to every other subjects that you are going to learn in this whole 4-year term. Okay, so it's related to like linking your real world problems to the theory aspect, and why we should look beyond the theory into what's actually happening and how it happens, why it happens. So now any discussion that happens on the electromagnetics or any problem that you see is first you will be facing a problem. That's when you look at like why that's coming up and how it's happening. So here I just put up one simple picture of a motor. So this is a picture of a machine where it's actual case where you might be having some burnout issue happening. Yeah, so there's a burning out happening on your windings front, and this is what you see actually when you break your motor down into pieces and then you look into it. Now, when you do a testing of that model, you will do testing to get out a lot of information. It could be certain electrical parameters. You will also look at the thermal aspect, like temperature. Evideyana choodu jaasti undo, any sort of melting can happen or not. So this is just a picture of the thermal scan. So what you see is that at one particular point you have very high temperature which is beyond the permissible limit. When you design a particular, be it a machine or any component that you have, there will be a constraint within which that design is built. There will be a set temperature constraint, there will be a set current constraint, certain parameters would be there based on which it is designed. So here what we see is that at certain point you have a temperature which is well beyond whatever is the given thing, and this is actually cause of the burning. So there was a high temperature generation because of which maybe your wire insulation burned out, and then you are seeing all these sort of faulty scenarios in your actual model. So there's a problem that you see when you go back and see why that happened. So one of the reason was temperature. Then you see why the temperature thing. Now, the thing is like you had all these burnout issues. formulas, understanding your systems, behavior, beyond that. So you have to go from just a formula based system to an equation understanding. So this tells you like when an equation is derived, what are the assumptions which are made, which can lead to a difference in your actual real-time model and the design model using it. So you need to have an idea of where the equation stops or what additional consideration has to be brought into picture. And then you move to a second level where you know what are the limitations of the equations. You can implement all those learnings and build on a newer system where you can make changes in your design. You can bring a more optimized, more updated models. And at the top level, you have master engineers who know what is equations, what is the theory. In real world, what are the differences that you have, what additional constraints has to be taken into account. And then you can uplift yourself to a set of engineers who know all these parameters, and you can use your learning to create a most optimized set of components or designs. So that's something like you have that understanding of where to start, what changes to be made, and where you can be. So we'll start with the major electromagnetic side. I know you guys have started with your semester. Can somebody tell me like what are the simple terms that you use in your electromagnetics? Some field quantity. In electromagnetics, what do you learn in your initial starting? No. No. Okay, inductance. Okay. Any other things? You learn about current, you learn about voltage. അതിന്റെ അപ്പുറത്തേക്ക് എന്താണ് പഠിക്കുന്നത്? കറണ്ട് കാരണം എന്തുണ്ടാവാം? മാഗ്നറ്റിക് ഫീൽഡ്. അതുപോലെ കറണ്ട് ഒരു വയറിലൂടെ പോകുമ്പോൾ അതിനകത്തൊരു കറണ്ട് ഡെൻസിറ്റി ഉണ്ടാവാം. അതുപോലെ തന്നെ കറണ്ട് പോകുമ്പോൾ അവിടെ ഒരു ഇലക്ട്രിക് ഫീൽഡ് ഉണ്ടാവാം. അപ്പം മാക്സ്വെൽസ് ഇക്വേഷൻസോ അത് ഇലക്ട്രോമാഗ്നറ്റിക്സ് പഠിക്കുമ്പോൾ first thing that you have is few terms. This is going to be discussed everywhere inside your electromagnetics. These are the basic set of terms which gets used everywhere or referred to. There are electrical quantities which are used. There are magnetic quantities. Electric side, if I say you have E, we call this electric field intensity vector. It's volts per meter, change in the voltage. So you can say how strongly charges are pushed into space. Then you have D, which is electric flux density. It's electric field including the effect of materials. So you have insulators, you can have a conductor, so copper. On the copper you have some insulations which are wound. Currently we put on these insulations. So what use in the insulator property and research fields mara. So you need to have an understanding of how that field changes because of this material thing. You know voltage, potential difference. So electrical height that causes charges to move. Then comes to the magnetic side. Magnetic side you have term like H, which is magnetic field intensity. So then you have V, which is flux density. So per unit area, what is the flux which flows through? That's given by the flux density. You have magnetic flux, which is the total magnetic field passing through a particular given volume or area. Then you have J, which is the current density, and you have rho, the charge density. So these are some of the terms which are going to be used when we discussed about the electromagnetics or Maxwell equations or its utilization. Are you familiar with these terminologies? Okay. So then we will move on to the Maxwell equations. Have you covered this part? Next semester. Okay. So when you get into discussion of electromagnetics. Okay. So when you discuss about electromagnetics, these are the 4 pillars, the 4 main equations that is that has to be known thorough if you have to understand what is electromagnetics, how a particular electromagnetic component works. So the 4 main equations that you have is one is Gauss law for electric thing, then Gauss law for magnetism, Faraday's law and Ampere's law. So these are the 4 different laws that will be used in the whole electromagnetic classes that you will have. Now what Gauss law tells you is, it's all about like how charges are created and how its motion happens. Charge creates electric fields. So you have a voltage source, how your charges are moving around that particular voltage source. This is something majorly defined by the Gauss law, and Gauss law defines the functioning of various components like your capacitors, you have insulations which are wound around the coil. The functioning of all these components are driven majorly by the Gauss law. Then you have Gauss law for magnetism. You have magnets, right? So you know how the flux lines around the magnets work. You take a magnet, you plot the vectors, you see there is a north pole, there is a south pole. Your vectors goes up, comes and returns and enters here. It goes around and enters here. So if I take a bigger box, you place a magnet inside that. So what you see is that whatever is going out comes and returns back. So here what it tells is del dot B is equal to 0, which tells that magnetic field lines always form closed loop. So it's always a dipole scenario. You have a north and a south always. You will not see only north or only south. So this is governed by the Gauss law, which says del dot B equal to 0. We will discuss in brief on like what is dot and what is a cross symbol and everything. I think you would have covered this in your vector calculus or some maths classes. Divergence and curl. So then you have Faraday's law. It gives you an information about how electric field is generated based on the magnetic field. We'll discuss these two in bit more in detail in the next couple of slides. So I'll not put a lot of effort here. Major thing that you can understand is Faraday's law decides the functioning of majorly transformers, generators, applications like induction heating and all. You have Ampere's law, which gives a relation between the current and its impact on the magnetic field. How a change in current will have an effect on the magnetic field generations. Okay. So here, okay. Before I go to the slide, tell me what does a divergence tell you? Del dot and the divergence. What do you understand from a divergence, or when you say a vector curl? What do you infer from that? That's a vector operation. When you say that some del dot A or X or Y, there are like why that dot comes up. What does divergence mean? Otherwise, curl is the cross symbol. Or a vector curl. Anyone? Okay. We majorly use the del or just an operator. But other scalar or vector, just an operation to be a del or a divergence, which is the dot product. Then you have curl. So then you have the curl. So that's a cross thing. So what divergence tells you is what flows out minus what flows in. Magnet example del dot B. Del dot B in a volume or an area, we say it is equal to 0. Why? For magnet either vectors that go and they come and enter back. So if you find a difference between them, del dot P, whatever is going out, it returns back. So that's why you say for a magnet example, del dot B equal to 0. So whenever you do a divergence, it means that you are finding out the difference between what is going out compared to what is coming in. So the example is your del dot B. Majorly in the case of magnets, if you take up, you say you have 0, or in any case, whenever you have a magnetic field which is generated, whatever is generated, the positive vector you define, you will have an associated negative vector with that. So these are some explanations on that. So you can see that for a source here in middle, if you are seeing del dot, let's say the vectors are majorly pointing outwards. So the sum of the difference between out and in is going to be a positive quantity. So you can see it's a positive divergence. And in this case, the other way. So how it goes? Then you have curl that comes up. Curl is more like how much does the field circulate. So there you have an equation like del cross H is equal to 0. So you know about the right hand thumb rule? So you have a current which is flowing. It generates the magnetic field that rotates around the coil through which the current is flowing. So you have the magnetics, the lines are represented by your fingers. So this is the curl that you have, the rotations. So curl operation when you do, it actually tells you like how much that field circulate around this particular source. So that's where you have the equation of del cross H is equal to G. So the current is linked with the magnetic field that is generated here. So when you write a del or a dot, it has a relation to the underlying physics that's happening over there. And these are just examples, like you have a current source, it generates a magnetic field around it, and this is a zero curl case because it doesn't result in the generation of a rotating field over here. Okay. So coming on to the Faraday's law. So Faraday's law tells you that del cross E is equal to dou B by dou T. So B is your flux density. So whenever you have a changing field, it results in the generation of an electric field. So now here if you see, this is a simple figure. Isn't this as a magnet? So it has a north and south pole assigned to it. And then the water circular you are seeing, this is a representation of a copper wire. So when you have a magnet which is generating a magnetic field, you try to bring it inside the coil, the circular coil. So the terminals of the in and out terminals of the copper wires are taken. You connect it to maybe a load resistor and you measure the current through it. So when you try to bring this magnetic field, the source, the magnet that you are having, you try to bring it inside this particular coil, it results in the generation of a current. Now, based on like the changes, so that's what you have, change in magnetic field results in the voltage generation, and faster you move, that is the dou V by dou T. The ratio when you are high, when you do a fast movement, it results in a higher current generation. So the faster the movement, then you have more turns. So more turns are the copper wires. So how closely you are packing in the turns, how many turns you have, all these decides how much of your voltage is reduced. The same, the Faraday's law, what we see here, del cross equal to dou B by dou T could be represented as voltage is equal to N is a number of turns that you have in the coil multiplied by dou phi by T. Dou phi is your flux change. So when you change the magnet, the flux that interacts with the coil changes. When this rate changes, your voltage is increased. So you can see your voltage is linked with your number of turns. It is linked with your flux, that is the rate of change of field. So this is what your Faraday's law tells you. And where and all you're going to use this law, you have it in your machines, be it generators or motors. You have it in your transformer. The generators, you see, you have a rotating magnet, changing flux, results in the voltage. Fine, like from a generator side. If you are using a transformers, you have a primary and the secondary. You pump current in the primary, it generates a field. That flux links with your secondary coil, and that results in the generation of a induced voltage or current in the secondary side. Now, induction heating application is something like you use for a welding purpose. That's another application, like you have two steel pipe, like magnetic pipes, you want to weld them. Then what you do is you take a coil, you pass a very high current through it. When you have a very high current at a high frequency, it induces, that's where Faraday's law comes into picture. It induces some back EMF or induced currents are generated inside your pipes. High current, I square R, you have a high losses. When you have high loss, it leads to high temperature. When you have high temperature, there is a welding that is happening. So induction is, heating is one field of like where electromagnetic is used in the manufacturing industry. So induction heating is another application where majorly Faraday's law is used. You have wireless charging, that is your transformers, where again this gets used here. And here if you see majorly the minus sign that you have, what does this minus tells you is, whenever you have a changing magnetic field, like when you try to move this magnet inside the coil, the current that gets generated inside the coil will produce its own magnetic field. And that will try to oppose this change. So that opposition is defined by that minus sign inside this equation, which is, you say it as a Lenz's law, which tells you the opposition part. So this is majorly on the Faraday's law. Then you will have Ampere's law. So Ampere's law, what it tells you is del cross H is equal to J. So that again is the same thing. So what do you see here? This is a cross section of a solenoid. So solenoid is something where you can see the application like a wall. Pipe mostly in pump sector and all, if you go, you have a pipe through which water might be flowing. You have a control signal based on which you decide when the water has to be, the wall has to be opened or closed. So what you do in solenoid is, it has a coil. When you excite the coil, there is a component inside this thing called as a plunger, which will move up and down. So this part will experience some force and it will undergo this motion. So when it moves up or down, bottom part, maybe a pipe might open or close. So actuators or solenoids, so it's just a cross section, cut section, like a 2D view is what I have put up here. So here what it tells you is, whenever there is a current, a particular part will experience certain magnetic field resulting in the generation of a force, which can lead to the changing position of that particular component. Is it going beyond? Are you able to follow? Okay, so more current, the stronger the magnetic field, more turns, stronger field. So few applications where Ampere's law plays a role are again motors, you have transformers, electromagnets, or inductors, that simple coil thing that you have. So these are few of the applications where it gets used. Now, one more thing that I would add here is, when you look into the Maxwell equations, you have Gauss, magnetic, electric, Faraday's, Ampere's law and all. Now, in every, if you take from an application point of view, you have motors, you have actuators, latches, so many things. Then you have radars, like when you look from an electronics point of view. You have radar, you have antenna. They also work on the same physics. But only thing is, here you handle 50 Hertz, 100 Hertz, maybe kilohertz. But when you go to antenna and radar sort of application, you get into megahertz, gigahertz sort of frequency. So frequency is too huge over there. Now the thing is, what people try to understand is, do you need this whole equation for all applications spread over this wide frequency range? So what people found out is, when you are operating in a low frequency range, you actually don't need the full Maxwell equation. That means mostly us who work on low frequency ranges or works on machines sort of applications, we don't have to use a full Maxwell equation. Why? The reason is, when you look at the wavelength of any particular signal, in our household we use a 50 Hz supply. That 50 Hz supply is used to excite your motor or any of these applications or models that you have. Now when you convert that into the wavelength factor, so wavelength is calculated as speed of light divided by the operating frequency. Speed of light is 3 into 10 power 9 8 meter per second. Frequency is 50 Hz. When you multiply this or divide it, you will get your wavelength like some 6,000 kilometers plus. And what wavelength tells you? It's how your waveform travels inside that model. What you have is a generator or a transformer or a machine. Maximum the size might be a meter, less than that. Unless you go to very high big generators and all, where the sizes are too huge. In general cases, your size might be sometimes in centimeters, maybe less than a centimeter, certain specific applications, or you have a bigger model. Here if you see a small transformer which is shown for a 50 Hz signal, when you compute your wavelength, that size is too huge compared to the size of the component that you are solving. So what happens is, you are not going to see any sort of radiation from this particular product. Your component is very well within that particular wavelength. So what happens when you take this particular aspect is, in the Maxwell equations, you have this term called as a displacement current. This you can actually dou E by dou T becomes 0 when you are in the low frequency range. So all of us who majorly work on electrical side, on motors or those sort of applications, the equation that we majorly deal with on the Ampere's law is a simplified version, which is del cross H is equal to J, and not the detailed one. But if you look at electronics stream people who work on radar antennas and other high-speed boards for communication, they solve the full equations. So this is something called as a full wave equation. In your syllabus, towards the end, I think you deal with full wave equation, computation and understanding. So that's where, so this thing, or if you consider the displacement current aspect, that's when you have full wave equation. Otherwise, what we use is more of a compressed version of that. And why we need to compress it is because of different, one we have discussed about the wavelength effect, another is from a computational point of view. Because simple equations means simple, you can solve your problems much more in a simpler version. And so now we'll move on to the next thing. So here, what we discussed about is all the fields and its usage. Here what I want to talk about is how your materials play a role in the system behaviors. For an example, if you are taking, like, you have an iron part, it's kept open to air. So you have discussed about your machines. You have a rotor, you have a stator outside, you have a coil which is wound on the stator. It generates a certain field, the flux flow from the stator to the rotor, the vice versa. In between them, the stator and rotor, what you have is an air gap. So the flux has to flow from stator to the rotor, crossing your air gap. So how that flux flow? So what you will always see is that the flux, when it flows from air to the material part, you will see always your flux converges into the material. So that's where, so what it shows us is like So minimum resistance path, or when you draw a simple circuit, you have a resistance network, you use a voltage source, you have one resistor here, 1 ohm, you have another resistor with 2 ohm. You will see maximum current flows through that 1 ohm resistance rather than the 2 ohm resistance in a parallel circuit. So minimum resistive path, the current flows. When it comes to magnetics, all your flux will flow through the minimum reluctance path. So reluctance is internally linked to your resistance aspect. So wherever you have minimum reluctance, the flux goes through that. And your magnet or this iron part provides that minimum reluctance part compared to the air that you have. So materials also has a very important role in how your system is going to behave. So these are few material properties, how it is linked to the magnetic quantities. So you know about BH curve? Okay. Normally how we draw, it started normal curve, you have B, it goes and sort of that slope changes and becomes steady. Why does that become steady? You have V axis, which is mostly in Tesla. You have H that you draw, ampere per meter square. The curve is more like it increases linear and then it goes steady. Okay. I'm not able to hear you. Any reason why it sort of that slope reduces? Somebody is saying somewhere. Saturation. Why it saturates? What is happening? Saturation is നടക്കുന്നത് പക്ഷെ saturation എന്ന് പറഞ്ഞാൽ എന്താ? ഇത് അടിസ്ഥാനപരമായിട്ട് ആ ഒരു കമ്പോണന്റ് അകത്ത് പല ഡൊമൈൻസും നമ്മൾ ആറ്റം എന്നൊക്കെ പറയുന്ന ലെവലിൽ when we draw the electromagnet കുറെ ഡൊമൈൻസ് നമ്മൾ പല വെക്ടർ ഡയറക്ഷനിലായിട്ട് മാർക്ക് ചെയ്യും. When you pump an external current, what is happening is all the domains are trying to align in a particular direction. The number of domains are fixed in a particular electromagnet. As you keep on increasing current, more and more vectors or domains will try to align in a particular direction. After a given point of time, you don't have any further domains. So everything has aligned. So your B, whatever you see inside, is almost stationary, or it reaches a saturation or a steady state sort of thing. So that's why you have that sort of curve that comes up. So what is that slope of that particular line, B versus H? That's what you define as a permeability or mu. So mu, if you see from a source point, mu is not constant. It's increasing when you have like more of a like increasing permeability or a slope remains same, and then it changes. So that's where the permeability or mu thing comes into picture. So mu, it actually tells us the ability of a material to support magnetic fields. So till one particular current magnitude that you are pumping, it can aid the magnetic field generation. Beyond that, no. It doesn't have more capacity to allow. So here you see a saturating field. Next, so these are for magnetic materials. Then you have conductors. So that's a copper comes in a bit. So inside copper, what you have is the current which is there in the copper is related to sigma and the voltage that is applied. That is I into R, interrelation that you say. So here sigma means that's rho is sigma, that's the conductivity of the material. How much it can conduct. So that defines the conductivity of like how much it can conduct a current. That's what sigma tells you. This again is a material property. So based on this material property, your J and E are decided. One could be input, one will be the output part that you have. When you take up insulators, the property of the insulator is defined by epsilon, or it is P is equal to epsilon E. So again, these are field quantities, this is a material property. And what does epsilon tells you is the ability of the material to store electric charge in that field. So these are all pure material properties. They are linked to your magnetic quantities, what you have. So what field gets generated when you give a voltage excitation or current excitation is also decided by the material property of that particular component that you are having. So now moving on to from equations to the problem, what what we normally do is, when you have any particular problem comes, design a motor or design a transformer, what all things do you need initially? Like if you look from a designer point of view, they will not even have the geometry. What their vendor might tell them is, I want you to design a motor of a particular power rating. It has to give so and so many torque at a given speed, and this could be the maximum dimension of that particular thing, from an axial length and from a circular radius point. These would be the basic input that a motor designer will receive. Based on this given constraint, the internal features, the structure, the type of machine, everything has to be decided. You have learned about DC machines, you are learning about synchronous machines. If you see synchronous machines, in synchronous machine itself, there are n number of type of machines that you have. You have permanent magnet machines. In permanent, you have something we call as an interior permanent, surface non-permanent. There are different types of machines that you have right now. Synchronous reluctance machine, another physics using which motor works. Now, once you get that particular brief input of the rating of the machine, first thing that you decide is, in order to arrive at that particular objective, first, what is the type of machine that you will use? That is decided by your application. If a fan and a motor and majorly for fan motors, nowadays you have BLDC sort of machines which are used in fan motor. And induction motors, so a lot of induction motor driven fans you have right now. So based on the application, you decide what type of motor to be used over there. So type decided. Adinishation, you will think on like what is the speed at which you want to run. For speed which it is 120 F by P, you know the frequency, you can find out the poles that has to be used. Lots of pole configuration. So you will arrive at multiple properties of that particular machine. Using, so all these things will result in a geometry creation. So based on the initial input that you had, came to the geometry selection, then you have to decide the materials. What material you are going to use. And then you will decide like what excitation, current ampere current pass voltage application volt. So you arrive at the excitation discussions. Now once you have all that thing, when you go into any sort of analysis, using all this information, you get into various tools which help you to analyze the component functioning. And once you do the analysis, you get some output. They will motor run negotiation for it, maybe 1500 RPM run pipe of giving a given current or voltage. You see what torque is given as an output by the machine. Is it in line with the spec that was given to you or not? So you check or validate your design based on the inputs which are provided. And then you have all your outputs. That's how you do all iterative studies. If you have not met your torque criteria, then you go back and redo the whole design by making some changes in the results. So this is the whole process of like how you solve a real world problem. Now here I have few applications on how you are going to link your equation with the actual model or real world problem. So this is one of the applications which I mentioned of a solenoid thing. So where you have a moving part, a coil, you have a outer core that we are having. The major objective is this part has to move up and down. So normally if you see in aerospace industry or in any aircraft that you will have lot of piping systems which pressure controllers, etc., where you will be using different types of these actuators or valves which will control the on and off of a particular switch. So now the thing that comes up here is like mostly you will be given a criteria saying that you need this open and close to happen in some given seconds or milliseconds. For a 3 mm distance move 5 mm distance move within 3 milliseconds or 5 milliseconds. So what you need is the moving part has to face certain enough force has to be generated so that this component moves up, and the movement should be, or the distance has to be traveled in that given time span. So how you going to link this actual problem with all that equations that you have is, you have your force which is derived, which is majorly a function of the flux which is generated there, and your current divided by the material property. So this, using these equations, you can arrive at like what could be the force that you can expect this part to face. Now you can take it forward to any simulation models or things like that, where you can build a virtual prototype of this particular system and find out what force it generates. Now what happens here is, like, initially the part was which is supposed to move is at this distance. So between the top portion and the moving part there is air. Air has different material property compared to the bottom moving part and the upstopper. As the component starts moving, the air region reduces. That means the resistance or reluctance between that part is reducing. So this time varying change in the material property will have an impact on what force that component experiences at every instant of time. So what is happening is that time is a factor. On the time scale, how your material property changes or how the system behavior changes is varying over there. Another application, if I take up like your transformers, so you mentioned about the leakage inductance calculation. Ideal is without any leakage, but in your actual system you are going to have leakage. What is the percentage of that leakage what you are going to have? What is the leakage inductance effect that you will see? So now you can link the functioning of your transformer with Faraday's law, which help you to understand the induced voltage in your different windings that you have. You can find out the voltages, you can find the leakage flux. So there are equations that you can use to arrive at the computation of different outputs which is expected out of the transformer. Now, now when you look at, so here whatever you see is two flux profiles, the flux density profile at two instant of time. So you are having an AC supply to your primary winding, so it's an oscillating signal. So you have a flux current which is starting from maybe 0, it increases. So when your current is increasing, your flux is also increasing. When your current decreases, your flux decreases. When your current direction changes, when it gets into the negative half, based on the right hand thumb rule, when your current direction is changing, your flux direction changes. Whatever was flowing in a clockwise direction initially changes into an anti-clockwise way. So here you can see at one point of time the density, the red, whatever the color you see are majorly related to the magnitudes aspect here. So when you have at one point the flux is high here, at another instant when your currents are changed, your flux are higher here. So on a time scale, if you see the field also, whatever you are seeing is going to change across this particular model. And another thing that you see is the flux is high in this corner. It's not there over here on this corner. So because of your reluctance path, your flux tries to flow through the minimum resistive path. What it tries is to flow close to this window rather than taking the longer path here. So what you see is your density is high in corners, which is closer to your coil. So you can see that sometimes maybe a saturation might happen here. So as a designer, you have to see like how you are going to, is it okay to have that saturation? Do you have to find some means to avoid that sort of saturations? So those are the things that you have to think and change in the design applications. Okay. Next is skin effect. So what do we mean by skin effect? Is it get to know skin effect? Okay. So skin effect. what do we mean by skin effect is ഒരു copper wire എടുക്കണം, current carrying copper wire, അതൊരു solid conductor ആണ്. അപ്പോൾ അതിനൊരു given cross section ഉണ്ട്. You are pumping a particular current through that. നമ്മൾ copper wire-ന്റെ dimension വെച്ചിട്ട് ഈ കൊടുക്കുന്ന കറണ്ടിന്റെ ഫ്രീക്വൻസി അനുസരിച്ച് copper wire അതിന്റെ ഡയമെൻഷൻ ഉണ്ട്, അതിനൊരു പ്രോപ്പർട്ടി ഉണ്ട്, അതിനൊരു പെർമിയബിലിറ്റി കണ്ടക്ടിവിറ്റി ഉണ്ട്. ഇതിനനുസരിച്ചിട്ട് what happens is like based on what frequency of current that you are pumping in, ആ frequency material property ന്റെ ഇതിൽ depend ചെയ്തിട്ട് current may pass through the whole cross section of the copper wire, like how you see this one. Yeah, ഈ ഒരു വീഡിയോയിൽ നോക്കിയാൽ at one these are frequency graphs. This is 100 hertz, 316 hertz, 1000 hertz and more. So at 100 hertz what you see is this is the current profile, current density. So at 100 hertz for this copper wire what has been used here based on its conductivity and permeability, what we can see is that full current is occupying the whole cross section. But when you increase your frequency, what happens is the current will experience certain opposition, the force, and it starts concentrating on the outer surface. But actual copper wire കുറച്ച് സർഫസിൽ മാത്രമായിട്ട് ഒതുങ്ങി നിൽക്കും. It will not flow through the complete cross section of that particular wire. ഈ പറയുന്ന skin depth എന്ന് പറയുന്നത് purely it depends upon the material property and the frequency. So when you design a particular component like copper wire or anything, depending upon the applications that you have, this is also something which you have to see. Because ഒരു വലിയ copper plate ഉണ്ടാക്കുന്നു, but you are pumping in a very high current. അപ്പോൾ current is just concentrated on some surface. ഈ copper plate എടുക്കാന്ന് പറഞ്ഞാൽ it is associated with some money. Somebody is buying it at some price, and for them reducing a millimeter thickness of that sheet will lead to some millions in saving. So selecting what size of that plate you are going to use or size of the copper wire that you are going to use has an impact. So from a designer point of view, you will have to see whether whatever size you have used is actually required or not. So that is another aspect that you will have to see. Okay, this is just an explanation on why it concentrates on the surface part. So here, for an example, like if you take a copper wire, for a given copper, so you have its conductivity and permeability that's going to remain same. പല ഫ്രീക്വൻസീസ് എടുത്താൽ ഒരു 50 ഹെർട്സ് എടുക്കുവാണെങ്കിൽ കിട്ടുന്ന ഡെപ്ത് എന്ന് പറഞ്ഞാൽ 9.3 mm ആണ്. ഒരു കോപ്പർ വയർ എടുത്തു അതിന്റെ റേഡിയസ് വരുന്നതെന്ന് വിചാരിച്ചാൽ ഒരു 8 mm ആണ്. So that means your skin depth is 9.3, but the size of the wire that you have taken is 8 mm. It means that through the whole 8 mm you are going to have current flow. A full copper cross section is getting utilized over there. But in place of this 9.3, assume you are taking some 15 mm radius. So radius is much higher than the actual depth. So depth is only 9.3. But 3 സ്ഥലം അതിനകത്ത് ഉപയോഗിക്കുന്നില്ല. Current is not flowing through that. Same is what you see. When you increase the frequency, your length, the depth keeps on reducing. And this has an impact because through a very small thickness, you are having the current flow. So initially 1 ampere ആയിട്ട് പമ്പ് ചെയ്യുന്നത് അതൊരു bigger thickness-ലൂടെയാണ് പോകുന്നുണ്ടായിരുന്നത്. അതേ 1 ampere you are pumping it to a smaller section. When you increase the frequency, same 1 ampere you pump it to a further smaller section. So when your area reduces, rho L by A, area reduce ആവുന്നു, length same ആണ്, material property same ആണ്, resistance മാറുന്നു. അപ്പോൾ ചെറിയ ഏരിയയിലേക്ക് കൂടെ കൂടുതൽ കറണ്ട് പോകുമ്പോൾ കൂടുതൽ ലോസസ് ഉണ്ടാവും. ലോസസ് കൂടുമ്പോൾ ടെമ്പറേച്ചർ കൂടും. ടെമ്പറേച്ചർ കൂടുമ്പോൾ മേ ബി അവിടെ ഫെയിലിയേഴ്സ് മെൽറ്റിങ്ങും അങ്ങനെ പല കേസസും ഉണ്ടാകാം. സോ ദിസ് ഈസ് അനദർ തിങ് ഓഫ് ഹൗ യു ഡിസൈൻ. I'll just skip this part. I'll come to something on like finite element analysis, or where I majorly my work concentrates on. So basics are electromagnetics. Now where does Maxwell, like how Maxwell equations, like in real time if you get into any design aspects, you get into any design of a machines, you cannot design a machine based on just the top level equations. There are a lot of underlying assumptions which are being taken. You have to overcome those assumptions and design a much more equipped model, for which we have in market a lot of methods or computational methods are available, which will help you to overcome those assumptions and design a much more optimized design. One of the method in that is called as the finite element analysis or finite element method. What it does is, when you did DC machine simulation, how was your DC machine represented? The stator linear represented. RS ഉണ്ടാവും, സ്റ്റേറ്ററിന്റെ റെസിസ്റ്റൻസ്, സ്റ്റേറ്ററിന് ഒരു ഇൻഡക്റ്റൻസ് ഉണ്ട്. നിങ്ങൾ ഇക്വലന്റ് സർക്യൂട്ട് ഡയഗ്രാം വരയ്ക്കാം. So then you are having a resistance for stator, resistance, inductance for stator windings. Then same way for rotor, some things you have rotor resistance, rotor inductance, or mutual inductance. ഒരു equivalent circuit resistance ഉണ്ടാവും. പക്ഷേ ഒരു മെഷീൻ എടുത്തു കഴിഞ്ഞാൽ അതിനാ കൊടുക്കുന്ന റെസിസ്റ്റൻസ് എന്ന് പറയുന്നത് ഇറ്റ്സ് നോട്ട് ഗോയിങ് ടു ബി എ സിംഗിൾ വാല്യൂ across its complete circumference. You would have multiple reluctance paths, വളരെ ചെറിയ ചെറിയ റെസിസ്റ്റീവ് നെറ്റ്വർക്ക്സ് ഉണ്ടാവും അതിനകത്ത്. Because at every point these factors are going to change. So that's where this method of finite element analysis came into picture. So what it ideally does is, any bigger geometry that you have, it breaks that bigger geometry into smaller shapes. Different tools that you have in market uses different shapes. Like here, if you see for this 3D model, it's a tetrahedron. So there are other tools which has on hexagon thing. So that shape, how you break your top level model is changing. So here, when you have it as tetrahedral component, so what you see is like this core part is split into some thousands or lakhs of elements, smaller sections. And what internal computation happens is, at each of this tetrahedron, what do you see? We call it as a mesh element. If you go and talk with your mechanical department people, they have much more in-depth understanding of what mesh is, what its importance, the shape of mesh, what do you consider, what is its importance. They do have much more in-depth understanding than we actually have as an electrical engineer, because we don't go in-depth in this aspect. So here what you have is, you actually break down the whole pieces into very, very small chunks, and then you try to see at each element level what is the resistance. So in your curriculum, what do you learn? You represent that whole stator windings as one resistance and inductance. Now what we do here is, we find that resistance and inductance for each of these tetrahedral elements that we have. That's much more closer to your actual model that we have than our classical way or electrical way that we follow. And when you do this analysis, it also it uses your Maxwell equations, all the equations, the Faraday's law, Ampere's law, everything is used, and it solves and gives you all those field quantities as an output. The flux density or current density values, all that comes as an output here. For an example, if you take up the electric motor. So this is an example of a permanent magnet synchronous machine. You have a stator, you have a rotor. Inside the rotor there is a magnet which is placed, we call it as an interior permanent magnet synchronous machines. In the stator side you are having the coils. The magnets are magnetized, you will have some north and south poles which are created here. Now what you are seeing is just maybe one eighth of that whole circular border. You have a full 360-degree view based on some symmetry. You see like how you have some sort of periodicity. ഒരുപോലെ കാണുന്ന ഏതെങ്കിലും ഒരു സെക്ഷൻ ഉണ്ടോ നോക്കും. ആ ഒരു മിനിമം സെക്ഷൻ യൂസ് ചെയ്യുക. That is rotated around the ball. So these tools help you to just use a simple section, whichever is that periodic part. So now, once you have this model, so from a operation point, you see you have Ampere's law, which tells like there is a current flowing through the stator. It results in the generation of magnetic field. Then what you have is a Lorentz force, which tells like There is a magnetic field which is generated. There is a current flowing through various conductors. The rotor experiences certain force, because of it starts rotating. You have again Faraday's law, where you have rotor which is rotating. That results in further changing flux in the stator. Back EMF, that results in limiting the speed at which your rotor is going to rotate. So all these things working together decides the operation of your particular machine. If I take up another example, this is the example. Okay. So I take this particular example. Now you all have phones. Majority of the phones that you are seen in the market is moving into a wireless charging mode. You have a charger separate, your phone is there, you no longer you have the wireless, you don't have the socket to fix the charging cable into the phones. You have all this wireless charging facility within your car, where you just go and place your phone on top of that charging pad, and then your phone gets automatically charged. So what happens beneath that? How it charges? So that's something majorly done by your wireless power transformer. These are also used for charging of certain electric vehicles too. Nowadays in our market, whatever you see, it has a plug for your scooters or for your car. Use a plug, connect it to the charging point, and that's how your car gets charged. There are cars which are also charged, or batteries which are charged using wireless transfer, where you bring in your car, your primaries are laid down on the track, you bring in, you get your car, park it on top of this particular charging point. Using the transformer basics, the battery inside the vehicle gets charged. So you have a transmitter, you have a receiver. So transmitter is, so receiver is on inside your phone, or it can be inside your vehicle. Transmitter is your charging pad that you are using. In the case of an electric vehicle, it's laid down on the road or on the charging table. In the case of your phone, it could be the charger that you get here, or it could be the vehicle you are placing it. Again, there you have a charging pad. So here what you see is that you pump certain current inside the transmitter. It generates certain field. That flux goes and links with the secondary or the receiver coil. Then there is an induced rate of changing field. It results in the generation of a current. So there is a magnetic field which is changing, resulting in the current generation. And that current goes to your battery. Battery gets charged. So this whole thing is again working completely on the electromagnetic side. Okay, I'll just skip this. So next, so those are all we discussed about the application aspects and everything. So you know what, this is just like what we have analytically, what have we decided based on if they are just using those equations and designing a machine, what happens and what you have to expect. So expectation or what you see in reality could be a bit different from what you will expect using the inferences from your equation modulings. So when you are going to learn, when you refer to your textbooks or any online materials that you have linked to those applications, it mostly when you look at the material aspect, these are just pointers, few pointers on where the differences will be, which can result in a difference between your actual model and what are you designing using just equations. One is on a material front, you have saturation effects, how saturation will have an impact, how permeability changes, how inductance is linked to permeability, and how that can lead to the current changes inside that model. So material property effect. Then you have temperature dependence. The magnet that you use has a pH curve. So magnet in pH curve, you will have a second quadrant. because it's a permanent magnet, you have a edge which is in the negative x-axis. Magnet or a given residual field in the in the second quadrant, when you don't have any external field, magnet they may have flux generating, which is normally we say is a residual field. And then external field external field pump magnet maybe that strength can change, operating load point to mara. Now this characteristic whatever you see for a magnet is very much dependent upon the operating temperature. Very magnet characteristic 20 degrees Celsius maybe it will give you a BR of some 3 Tesla. This 20 100 degrees Celsius the 3 Tesla field will drop to maybe 1 Tesla or 0.5 Tesla. But temperature has a lot of effect on the magnet function. Now you are going to use this magnet inside a motor. Assume this motor is used in an electric vehicle. That vehicle can run in Sahara, it can run in Alps or in any cold country that you have. So this motor is supposed to function at 45 degrees Celsius as well as it is supposed to function in somewhere close to 0 degree or minus. So you have to take the effect of this temperature. How this temperature is going to have an effect on the magnet property, in turn on the motor functioning and the final output of that particular machine. So our efficiency aspect, how efficiency changes, temperature and efficiency our understanding couldn't die. You should think from that perspective. So that was the temperature aspect. Next is like motor and electronics. So you have a motor, you have current flowing through the coil. I square R losses. Stator, rotor, and you have core loss. What is core loss? Any current hysteresis combined with the core loss. Above core, stator, rotor, loss. Windings magnet magnet induced current losses. These losses of endowment losses can result in temperature. Maintain the temperature item. Temperature item what will happen is you can have burnout issues. Or else what will happen is temperature material strength reduce. Strength we can bend it up. Temperature material strength variations. Our variations structural impact. Machines in the case rotor rotate. For rotor rotate, this is going to experience some force because of which it's going to rotate. Our machines have slots or teeth that gets created there. These teeth portions the force that it experiences can lead to other changes shape teeth in the position electrical phenomena that resulted in some temperature generation. That temperature generation altered the strength of the material that was resulting in some breakage. So what you will actually as a manufacturer you might see a broken piece. The thing is why it broke. Multiple reasons you will put it out. So then you keep on, you do one checklist. One was some structural issues, some magnetic thermal issues, then electrical issues. So you come down and you find out it was the electrical characteristic that was resulting in this fault. So understanding of all these underlying things is important. So that was on all that equations, what equations, where it is used, how that is getting used into various applications that you see, and we discussed about what is there in your textbooks and then what you can actually expect. Like how as an engineer you should go beyond the limitations of your equations have much more in-depth understanding of that component. Because like, see, nowadays what we normally see is that somebody just thinks from mostly a box perspective. You are inside that box. You look at only from electrical point. That's not sufficient. You should look beyond that box. Only then you are going to have a clear perspective of what happens for that particular component or that system. So as an electrical engineer, you should look beyond the constraints of that electrical thing. Because somebody, a mechanical engineer might come and tell you that something has broken. You might say, that is not my headache, that's your headache. There is structural part, you decide why that. You have no material, part so that is a reason. The reason for that failure might be something that you designed, an electrical design that you did. So you have to connect the dots and see where you are placed, what you can contribute. So all these you have to do, you need to have an in-depth understanding of your physics. The EMFT in the subject is very difficult to understand. But unlike our scenarios that we had, you have lot of needs to learn. See, EMFT is a question is visualize what is happening underlying, visualize we were referring to textbooks. Now you have all these LLMs, ChatGPT, Gemini, three platforms on it. You go and put up any of your text questions that you have, you want to visualize, you put a command there, it will give you pictures or videos that you have. You can understand, you have options to learn and understand more about what you are learning. That will give you a much more broader picture. So utilize that. And for this one, see, I put up some names on the textbooks and all. This may or may not be required. These are just some textbooks which will give you much more details about what is electromagnetics, how it is used, more underlying at the core level, how all this physics works and how it's derived. So these are just list of some topics, textbooks, some online courses which do provide you on classes on some electromagnetics. There are NPTEL videos which are there, which you can use to learn more about this particular tool. And then you have softwares. So software side is open softwares, open source softwares അത് ഫ്രീ ആണ്, നിങ്ങൾക്ക് ഡൗൺലോഡ് ചെയ്തിട്ട് അത് യൂസ് ചെയ്തിട്ട് കുറച്ചൊക്കെ പഠിക്കാൻ പറ്റും, കുറെ അറിയാൻ പറ്റും. അതല്ലാണ്ട് തന്നെ പിന്നെ കുറെ ആൻസസിന്റെ ടൂൾ, ഞാൻ വർക്ക് ചെയ്യുന്ന പോലത്തെ കമ്പനികൾ, അങ്ങനെ ഒത്തിരി കമ്പനീസും ഉണ്ട് മാർക്കറ്റിൽ. അപ്പൊ അങ്ങനെ പല കമ്പനികൾ പ്രൊവൈഡ് ചെയ്യുന്ന അവരുടേതായ കസ്റ്റമൈസ്ഡ് ആയിട്ടുള്ള ടൂൾസും ഉണ്ട്. You can use of any of these resources, the open source resource that you have, all the textbooks or whatever knowledge is available in net on internet. And the last thing just I want to add is like we discussed about multiple applications, where it is used, physics and all those things. Just want to list out like which are the applications, what are internal applications that you have, which companies are there where these are getting utilized. Because you need to know, like, if you learn, if you devote your time and energy to understanding something, where are you going to use that? So, if you try to learn more about vehicles, the traction motor side, onboard chargers, wireless charging, power electronics, there are a lot of companies. These are just few of the companies that you have in the market. There are companies like Tesla, BYD, Rivian, Lucid, lot which are there in India too. They do day in, day out motor analysis, they do day in, out transformer simulations, electronic transformers. See, when you say transformers, you look at more that big transformers, power transformers. Transformers are not just power transformers. You have transformers inside your simple circuit, inside your chargers, flyback converters. Inside that you have small electronic or planar transformers and all that comes out. So at that miniature scale too you have transformers. So don't think that transformer means it's that big transformers that you have. So these are some companies. When you get into power electronics, you have converters, inverters. I didn't touch base on emergency because this is a very complex top-level thing. Inverters and everything. These are some of the companies where you have opportunities for these sort of background people. ABB, Siemens, Schneider, Delta, TDK, they all work on transformer design, they all work on inverter, converter designs and everything. You have renewable energy where you have again generators, solar inverters, energy storage system, the companies like Vestas, renewables, Enphase and all. If you look at industrial automations, applications like servo motor design, sensors, solenoids or actuators, these are majorly designed by companies like Bosch, Honeywell, Rockwell. You have all of them in India, different parts of the country. They all work exhaustively on these physics and these bonds. Okay, so these are just some popular companies where it is used, and all of them, look at people who have that background knowledge. അടിസ്ഥാനപരമായ basic knowledge ഉണ്ടോ ഇല്ലയോ എന്നാണ് നോക്കുന്നത്. And one more thing to add up is nowadays if you see things are all moving into all AI. Artificial intelligence എന്ന് പറഞ്ഞിട്ട് ഇതിലേക്ക് പോകുന്നത്. അപ്പോൾ വരുന്നതാണ് automation. Okay. So build yourself to like work on developing yourself, learning Python, അങ്ങനത്തെ coding languages. Okay, you might have those topics as subjects ഉണ്ടാവും പഠിക്കാൻ. Later, take your time, learn those topics because that are going to be very very useful going forward. Python ഇപ്പോൾ ഒരു hot topic ആണ്. എവിടെ നോക്കിയാലും automation എന്ന് പറഞ്ഞിട്ട് അതിനു വേണ്ടി യൂസ് ചെയ്യുന്നുണ്ട്. അപ്പോൾ ഈ കാണുന്ന ഞാൻ എന്തൊക്കെ കാണിച്ചിട്ടുണ്ടോ ചെയ്യുന്നുണ്ടോ അതൊക്കെ പല കമ്പനികളിലും when it is more of repeated things. ഒരു ജോമെട്രി എടുത്ത് പല സ്റ്റെപ്സ് ചെയ്ത് അനലൈസ് ചെയ്ത് ഔട്ട്പുട്ട് കിട്ടണം എന്നുള്ളത് റിപ്പീറ്റഡ് ജോബ് ആകുമ്പോൾ those are all automated. So Python വെച്ചിട്ട് നിങ്ങൾ ഫുൾ ഓട്ടോമേഷൻ ആണ്. പക്ഷേ when you have to work on some innovative designs, repeated അല്ലാതെ പുതിയ പുതിയ കാര്യങ്ങൾ ചെയ്യണമെന്നുണ്ട്. That's why you need those knowledge to do or work on more innovative things. So have your basic core knowledge. On top of that, try to learn these languages because that will help you in a longer run. Because that's something that we are seeing in the market. Everybody is moving towards automation, AI, and all those things. So together with those basic things, learn all those things. So these are something that I wanted to cover in this 1 hour thing. Hope something went into your head. I know it's a bit tough. ഒത്തിരി കാര്യങ്ങളുണ്ട്. Maybe some idea. So all the things doesn't have to click in your get stored in your head. But at one point of time you can think like, okay, that day I saw something or heard something. You Google it, you get that. So now you don't have to Google it. You can go to ChatGPT or any other thing, and you'll get the results. Okay. So any questions? എന്തെങ്കിലും ചോദിക്കാനുണ്ടോ? എന്തെങ്കിലും doubts? എന്തെങ്കിലും? Okay. സാധാരണ അതിന് ചോദിക്കാനുണ്ടോ എന്ന് ചോദിക്കുമ്പോൾ പറയും ഒന്നോ നിങ്ങൾ എല്ലാം മനസ്സിലാക്കി ഇല്ലെങ്കിൽ ഒന്നും മനസ്സിലായില്ല. EMFTന്റെ കേസിലാവുമ്പോൾ എന്തായാലും രണ്ടാമത്തെ ഓപ്ഷൻ വരാനേ കൂടുതൽ ചാൻസ് ഉള്ളൂ. ബട്ട് just try hard, try to learn your subject, get more information about what's happening. Don't just learn for exams. It's important, but on a longer run, the basic thing is what is more required. Okay. So that's me. So thank you everyone. Just ending with one liner. So it's more on the electromagnetic side. The most profound insight in the physical science is that everything is ultimately electromagnetics. From the structure of atoms at the very core part to the operation of machines to the transmissions of higher signals. So you know how Maxwell equations works. What those field quantities are, you can work on any application which is related to electrical or electrical or electronics things. Okay, yeah, that's all from my side.
Anybody willing to share feedback? Anyone?
എന്റെ ഇത് ഉദ്ദേശം ഞാൻ ബിടെക് കഴിഞ്ഞു. അത് കഴിഞ്ഞ ശേഷം 2 വർഷം പഠിപ്പിക്കാൻ പോയി. അത് കഴിഞ്ഞ് ഞാൻ എംടെക് ചെയ്തു. എംടെക് ചെയ്തിട്ട്